Now let's think about how we can use Newton's second law to actually figure things out in any situation that involves forces and accelerations. Well, let's look at an example first. Got a skydiver falling. So velocity points down, and the skydiver, even though the parachute is open, the skydiver is still accelerating, still speeding up, just not speeding up at the free fall acceleration of 9.8, accelerating much more slowly, because what the parachute does is create a really, really strong drag force on the skydiver. And the question we would like to figure out is exactly what is the acceleration at one particular moment during the dive, and at that particular moment the magnitude of the drag force is equal to 0.8 times the skydiver's weight. Remember, one strange aspect of a drag force is that it gets stronger as the speed increases. So when the skydiver is accelerating, and of course the speed is increasing, then the drag force keeps on getting stronger and stronger, and at one point it'll have increased until it's equal to 80% of the skydiver's weight. So how do we do this? First, we don't look for an equation, because in a sense we know what the equation is. It's going to be Newton's second law. It's going to be a particular version of Newton's second law appropriate to this particular problem. And what that version is tough to figure out unless you first try to understand the problem as clearly as possible. And understanding begins with a free body diagram, just arrows to represent the forces, in this case only two forces, weight and drag force, and then signify which way is the positive and which way is the negative direction in your coordinate system. And I'm choosing down as the negative direction because down is the direction of motion. Direction of motion, we like to choose that for the positive direction in a coordinate system a lot of the time. And then of course one more thing, in a free body diagram we want to include an arrow that shows the direction of the net force. The skydiver is accelerating, so there is a net force. And the net force will point down. Whenever somebody is speeding up, velocity and acceleration point the same way. So in this case, the skydiver's acceleration is down, and always, this is a consequence of Newton's second law, always acceleration points the same way as the net force that is causing that acceleration. So here's everything we know, everything we understand about the problem. The next step is to turn this diagram into an algebraic statement. Algebraic statement meaning that I use these algebraic symbols for the two forces. Turn it into an algebraic statement that shows how the forces combine to give you the net force. And the simple way of combining all the forces is to just say we add up all the forces in the positive direction and subtract all the forces in the negative direction. In this case, there's only one force in the positive direction, and then we subtract the one force in the negative direction. Notice what I'm doing here. Fd is the magnitude of the drag force. Fd is a positive number, and I use the fact that I take into account the fact that the drag force points negative by subtracting that magnitude in the algebraic expression for net force. And since it is a net force, Newton's second law tells us that it has to equal mass times acceleration. And of course, acceleration is what we're looking for. Now we use the fact that the magnitude of the drag force is 80% of the weight, so we have weight minus 0.8 weight, that's the drag force, equals mass times acceleration, or subtract away 80% of the weight, and you've got 20% of the weight. 20.2 times the weight equals ma. Now remember, weight is a force equal to mass times g, the acceleration due to gravity. So I can rewrite this w as m times g. And what I have now is this 0.2 mg equals ma. And conveniently the factors of mass cancel out. Convenient because we don't know the skydiver's mass. And all we have now is 0.2 g equals the acceleration. 0.2 g equals the acceleration. And since g is 9.8 meters per second, 0.2 times g is 1.96 meters per second. That's the acceleration of the skydiver at this particular moment. The skydiver is still gaining downward velocity, but the skydiver is going 1.96 meters per second faster in each second. So what did we do here? There are basically three steps. First, understand the problem by drawing a free body diagram. It should include an arrow for the net force. That's helpful. And labeled arrows to indicate all the forces and indicate which way is the positive and negative direction in the coordinate system. That's important for the next step, because when in step 2 we write this algebraic expression that shows how the net force, how you get the net force from some combination of the individual forces that you wrote down here. And the right combination is always add up all the forces in the positive direction and subtract all the forces in the negative direction. And then once you have that algebraic expression, since it is a net force, it's equal to mass times acceleration. And then the third step is just to do whatever algebra is necessary to get your answer. Algebra plus sometimes using a few other facts that you might know. In this case, we had to use the fact that you calculate the weight as mass times g. Now here's one more example, and before I do that example, let me describe one little complication with rolling friction. There'll be some rolling friction in this question. So think of a car. And let's say the car is moving this way. And let's say it's a rear-wheel drive car, so the engine sends energy to the back wheels, but not the front wheels. So when the front wheels roll, they roll just only because rolling friction is making them roll. If there were no rolling friction, the front tires would slide this way, but sliding this way is being prevented by rolling friction, makes the tires roll instead. And in order to prevent a slide this way, the friction force has to point the other way. So there is a backwards friction force acting on the front tires, a rolling friction force, and I'll just call it BAC for a rolling friction force that points backwards. This works differently because the engine is sending energy to the rear wheels. These wheels always rotate, no matter what else is going on. And when the rear wheels are always rotating, two things could happen. If this was a really, really icy surface and you were not able to get the car moving, it was stuck here, these wheels would just spin in place. And that is the piece of the tire that's in contact with the ice would just slip that way, and the car wouldn't move. So if there's ice, or in other words, some kind of surface with really no friction to speak of, the back tires will just spin, or you could think of it as this little piece of tire in contact with the ice is slipping that way. But if these wheels are rolling normally, this kind of slipping is prevented, and you get rolling instead. And in order to prevent a slip or a slide this way, again, rolling friction has to point opposite to the slip or slide that it is preventing. So rolling friction on the back excuse me. I had that backwards. So the wheels are going to rotate counterclockwise, no matter what, whether the car is moving or not. And so if on an icy surface they're stuck and the wheels are just slipping, the slip is backwards. And so when the wheels roll, instead of just slipping like that, rolling friction is preventing slipping, and rolling friction always has to point opposite to the slip or slide. So the rolling friction on the rear wheels points forward. That's actually going to be the force that speeds the car up, gets it started. And I'll call that a rolling friction force F. It's the rolling friction force that points forward. So now, imagine a car with a mass of 1,500 kilograms. And it feels a bunch of forces. The rolling friction that points forward and is really the one that's responsible for accelerating the car forward. It has a strength of, let's say, 15,000 newtons. And the backwards pointing rolling friction force, the rolling friction force that's acting on the front tires, has a magnitude of 2,000 newtons. And the car is going fast enough that there's a significant drag force. That drag force has a magnitude of, let's say, 10,000 newtons. And we would like to know, what is the acceleration of the car? We're going to do all the same things that we did in the first problem. First, draw a diagram that shows all the forces, shows the net force, shows the positive and negative directions of our coordinate system. So, in this case, all the forces on the car, there is, of course, weight pulling down and a normal force from the road pushing up. And there is the forward pointing rolling friction force, the rolling friction force on the back tires. And then there is the rolling friction force on the front tires, a force which points backwards. And then there is drag force. Drag force always points opposite to the velocity. And we're imagining the car is moving this way. Velocity is that way. And the car is speeding up. So, again, if something is speeding up, acceleration points the same way as velocity, and net force always points the same way as the acceleration because it causes the acceleration. And since the net force is horizontal, the acceleration is horizontal, nothing is happening vertically. So the only forces that we have to worry about are the forces that combine to give us a horizontal net force. Nothing is happening vertically here. And so, what's the algebraic expression that, that shows how all the horizontal forces combine to give us the horizontal net force, or the horizontal component of the net force, if you want to talk that way? So, net force is all the force in the forward direction added up. There's only one forward force, the forward pointing rolling friction force, and then subtract all the forces pointing in the negative direction. Again, I've chosen to put the positive direction in the direction of motion. The car is moving to the left, that's the direction of motion, so I'll make left the positive direction. And there's only one leftward force, only one forward pointing force. And there are two forces pointing in the negative direction, so you subtract them when you write down the net force, minus rolling friction that points backwards and minus the drag force. And of course, being a net force, it has to be equal to mass times acceleration. And at this point, we can put in some numbers and figure out what the acceleration is. The rolling friction was 15,000 newtons. The forward rolling friction. The backwards rolling friction was 2 at a magnitude of 2,000 newtons. And then the drag force at a magnitude of 10,000 newtons. And that's equal to the mass times acceleration, and the mass of the car was 1,500 kilograms times A. Well, 15,000 minus 2,000 minus 10,000, that gives us 3,000. All this just comes out to 3,000, and that 3,000 is equal to, or 3,000 newtons, and that is equal to 1,500 kilograms times acceleration. So just divide both sides of the equation by 1,500 kilograms, and you come up with an acceleration of 3,000 divided by 1,500, that's just 2. 2 what? 2 meters per second for the acceleration. Questions will get more complicated as time goes by, but every one of them goes through these same three steps. Draw pictures so that you know what the forces are and what direction they point in, then use that information to write down the algebraic expression that shows how the forces combine, add all the forces, subtract all the forces pointing in the negative direction, and that's the net force, so you set it equal to mass times acceleration, and that way you've got an equation that you can usually solve for whatever it is you need to solve.